Hi everyone, my name is Raina, and today I'll be presenting on our project, Dislocation Properties and Mobilities in Titanium via Molecular Dynamic Simulations. I'd first like to thank my sponsors, Los Alamos National Laboratory and the online OREU program at Texas A&M University, as well as my mentors, Dr. Tung, Dr. Nuttall, and Dr. Fenson. Since we're studying dislocations in titanium, some background on the importance of this. Specifically, we're looking at titanium because it has high strength and low weight, so it's used in many applications such as in the aerospace and automotive industries. As shown in the figure on the left, titanium is widely used on aircraft. Dislocations are a type of material defect. So not all materials in life consist of perfect crystals, so there are always going to be defects. They are the weak points of the material, so failure is often caused by the defect moving as opposed to breaking every atom's bond in a material. Dislocations especially grow and move as a material is deformed. So studying the properties of dislocations as we deform titanium allows us to better understand its failure mechanisms to prevent situations like these on the right. This is an overview of what we use to do this project. In the next few slides, I'll go deeper into these tools and explain why we're using them, but we are using molecular dynamic simulations. We're using LAMMPS code to set up the simulations and control parameters. Then we're running these simulations through supercomputers, and lastly, to look at the data, we are using Python as well as OVITO, which allows us to visualize the atoms. So firstly, I mentioned the use of simulations. So why simulations? Analytical solutions don't exist for most problems, and physical experiments are extremely difficult to control. In this video here of dislocations moving through a material, you can see that once they get moving, they disappear pretty quickly. So it's small, and it's occurring in a really short time, which means you have a very small window of observation. Simulations are much easier to control and study the results of. The figure on the right shows simulation methods for different length and timescales. For studying dislocations and looking at individual atoms, we typically deal with pico to microsecond timescales and microns in length. So simulations are the best way to study that very local behavior. I also mentioned that the simulation method we're using is molecular dynamics. So in MD, all the atoms in the material are treated as point masses that interact with each other. The figure below briefly shows the steps involved. So firstly, it requires inputs, which include the inner atomic potential and some initial conditions like initial position, initial velocity. Then it takes those conditions and for a really small time step, integrates the equations of motion and outputs quantities like temperature. It also solves for a new position and new velocity, and that's used as the new initial condition for the next time step. And then it integrates the equations of motion again, and it keeps going for small time steps, and as a result, you have data for how atoms behave as a function of time. I mentioned the code that we're using to control the simulation is LAMMPS, and it was created by Sandia National Laboratory. It's open source, and there are many resources out there. Here's an example of some lines of code. As you can see, you have control of many parameters. LAMMPS is also really good for large-scale problems, so simulations that require lots of computing, like ours. I mentioned running these through Texas A&M supercomputers because we need their advanced computing resources for large problems like these. Now to titanium specifically. So first I'm going to give an overview of what we did and then show the results on the next slides. So we deformed titanium in tension, compression, and shear, visualized in the animations here. We loaded the stresses in the X, Y, and Z directions, X, Y, X, Z, and Y, Z for shear, and at temperatures of 10, 300, and 600 Kelvin. So 3 loading types, 3 loading directions, and 3 temperatures. All these cases were done while fixing the other parameters. I talked about a potential file being required for molecular dynamic simulation, so we use this potential file here. This is a screenshot of just the first part of it, and we picked the one most appropriate for the conditions of our simulation. Lastly, our simulation box consists of a bit over 200,000 atoms. So results. Firstly, let's look at the effects of temperature. These stress strain curves show one case of tension, compression, and shear, this case fixing the stress to act in the Z or YZ direction. Temperature clearly has an effect on how quickly the material yields and fails, and this is expected. These differences were also observed in the cases not shown on this slide. Next, we'll look at the effects of loading direction and loading type. Here I'm fixing the temperature to be 10 Kelvin. Again, we're looking at tension, compression, and shear, but now comparing loading direction. So each color represents loading in either the X, Y, or Z direction. For all the cases we looked at, including those on the slide, titanium appears to be anisotropic. In other words, the properties are different depending on where you apply the force. Also, when we talk about directions like X, Y, and Z, the visual down here shows what is meant by that. So titanium's crystal structure is hexagonal close packed, HCP, so it looks like this, and so the X and Y directions are here, so along the same plane of atoms, whereas if you move in the Z direction, you're moving between planes of atoms. It's important to keep in mind also that these results are more qualitative. The quantities in these graphs, like the ultimate tensile strength, isn't going to match what you get if you took a chunk of titanium and pulled it, because these are overestimates. And that's because our simulations start with perfect crystals and then we deform them to turn them into imperfect crystals. But in reality, the material never starts out perfect. However, the relative quantities here do give us a lot of insight. Here, it's clear that there's a lot of variation in mechanical response depending on direction and type of load, and this tells us that we have to look deeper into the microstructure of the material. So now we're going to zoom in on the tension case and at 10 Kelvin, because at this low temperature, there's less thermal vibration, so it's a lot easier to see what's going on in the animations I'm about to show. So first, let's look at the X direction. The graphic on the right is generated using the software OVIDO. The box here is our simulation box, so this is our chunk of titanium. In this animation, I removed any atoms that had HCP structure. So in other words, an empty box means it's perfect titanium, while anything you see, like the blue or gray, those are defects. So this is what it looks like as it's deformed in tension. Now, looking at specific points on the graph, this point corresponds with the image here. So at this point, all atoms are still HCP structure. Next, you can see a couple atoms. Those are BCC, so body-centered cubic, which means they have taken on a new structure. On to the next, you see lots more blue, and we conclude that there is a stacking fault on the 1,2-bar-1,0 plane, and a stacking fault is a type of defect and just means that the atoms are not arranged or not stacked the way they're ideally supposed to be. Now we look at the Y direction, same thing over here, just a couple of atoms. As we move on more and more, and there's a stacking fault on the 101-bar-1 plane, so a different plane from the X direction. Z direction, again, it looks different, but the plane is unclear. So to conclude, we looked at the effects of different loading types, loading directions, and temperatures, and we conclude that titanium is anisotropic. So there's a strong connection between microstructure and mechanical behavior. What that means is if we look again at the stacking faults for the X, Y, and Z directions of titanium in tension, it's clear that the way the defects nucleate are different for each case. So if we look at the stress strain curve, it's clear that what's happening on the atomic level influences the bigger picture mechanical behavior. For example, for the Z direction, the plane is unclear and we kind of see blobs of atoms, and that then corresponds to a much higher stress strain curve. So it takes more energy to nucleate defects compared to the X and Y direction. This emphasizes again that there's a connection between the microstructure, those tiny defects that exist, and the large-scale behavior. In designing materials or choosing materials, a lot of times we look at large-scale properties, and that's like actually the average of everything that's happening on a tiny scale. And sometimes that's overlooked, which is why studying small-scale behavior is important, and it's evident here in our results. And that's motivation for future work, like adding defects to the material before deforming it and examining properties of individual defects, because this will allow us to further study the microstructure of titanium. And that concludes my presentation. Thank you.